an excel or they call it technology as in Europe. They have managed to help more than 500 businesses across the globe really reaching the potential. And that's the reason why we just recently got Series B funding, right? How about the Series B funding?
Yeah, we just closed the round in July.
So please welcome Theo himself and the founder, Nikita.
Thank you guys. Let's see if I can run this down. Welcome everybody. Thanks for coming. Thanks for staying for the last presentation. My name is Nikita. I'm from Yahoo GridGain-In. So what I want to talk to you for the next 30 minutes is about in-memory acceleration for Hadoop. And as the community of vendors and customers, we went away from the stage where Hadoop, we can tinker with the prototyping in a couple of years. We're now moving to a stage where a lot of companies are trying to move Hadoop close to operation layers to result in yield and processing. And about a year and a half ago, we started hitting some of the typical problems with Hadoop about performance. And by now, there are a number of projects available where we trying to fix this issue in different ways. All-in is a single project trying to fix the indexing in the SQL serial edge-based and pretty powerful and high-performance database and there's a project like Storm, for example, that's something similar to what we do. I believe at GridGain, we have a fairly instant take on how to integrate Hadoop. We just recently announced the product, in-memory extended for Hadoop, part of our whole in-memory system products. So hopefully the next 30 minutes we'll be easy to take a look at it and do some quick overview of what it is. I'm not going to spend too much time on this slide, but I'll understand what Hadoop is. It's a batch-rented system, 2D technology, HDFS, and MapReduce. We move data ETL in and out of it. So MapReduce is essentially a framework for composable jobs to run parallel on the data stored in HDFS. There's the nested system of projects and products around it. We use DW. Project very simple, scales very well, resilient, extremely resilient, very accurate system. Really targeted for large historical data sets, terabytes and petabytes. Now the cons is where things get a little bit interesting. It is a batch-rented system from a get-go, and that's how it was designed by Google a decade ago. That's how it was started by Yahoo. Well-known history. So real-time is simply not possible. The stock Hadoop, you cannot get low latency real-time processing, not because engineers are not capable. It's just what the design was from the get-go. Hadoop suffers, in my opinion, from fairly complex one. If you look at Hadoop 2 or 3 years ago, it used to take about a week report. It's gotten a lot better right now. But you're still suffering from name-node, awkwardness, and all the different things in the Hadoop system. There's significant institutional overhead. Anybody who wants to have these jobs and try to optimize them for performance is most important. It seems like the whole GDM for in the prospect and on and on. Sometimes the overhead can be set just to launch it fast. Now the HDFS is very long. It is a disk-based system, although it's a disk-based system. And if the player has to put the flash behind it, it didn't really help much. And you still get to suffer the same disk-based bottleneck. On the left side there, on the bottom, there's a diagram of overall fusion in Hadoop. And remember this diagram because you're going to be looking at this diagram throughout the presentation. It's a very typical diagram. There's a user application on the left side. It's a data job tracker, task tracker, name node, data node, and it is very behind the diagram. How execution happens to Hadoop. So we're giving you a little bit of overview, very high level, what have we done in-memory accelerator. So we're literally, so to speak, attached to two major components. If you want to accelerate things in Hadoop, you have to do something with the file system, and you have to do something with the memory. So we started with developing a industry-first in-memory file system, massively distributed, fully HDFS compliant in-memory file system. It's a very interesting project. As you know, HDFS is a lot more components of the file system. So we developed the first in-memory file system. It significantly boosts performance of HDFS. I have the benchmarks down the bottom of the slide. Think about this architecture. Think about a memory first versus disk first architecture. Think about this example. What if you want to read a record in your application and you have a disk file system? So what happens to you in Java? So you usually request to read the record. It goes to the operating system I/O. Then it goes to the I/O controller. Then it goes to the device. There's a C-time device. All the way back to the center points. And then it would have to be marshaled because you're in the device stream. And they have to be marshaled in the object. It's a fairly long process. Now think about the same example when you have in-memory data, like a memory file system. You want to read a record about the only thing you do. You do the pointer directly. You move in the pointer to the application memory in the same process. And you get the data, and there's no marshal. And you marshal, you get exactly the same format as you need. That's fundamentally where you get in this typical 10,000x performance difference when you get in-memory versus on disk. By the way, if you do the flash doesn't work really well, because when you flash, you don't recognize that C time motion us. You don't really do much about buffering, marshalling, IOs, or SIO, and IO controls. So we put a lot of performance on that, just this very basic fact. The memory file system that we developed works uniquely in two modes. It can work as a standalone file system. You can literally drop and replace HDFS by one memory file system, no changes to the core changes. It can also work as a cache in front of the secondary HDFS. And I'll talk about this use case further down the road. Memory use. Obviously, once you have data in memory, in the memory file system, typical good memory use wouldn't work very well. It was designed for it. So we typically step at it and re-optimize the memory use. We work on the data that is in memory. And the combination of those two gives you, on average, I would say 10-15x performance without any step. On some of the tests show 100x performance with the same memory use just we can run for that memory use. So in memory use, we eliminate the entire overhead of memory use. Look at this picture on the right side. The hidden blocks is your typical workflow in Hadoop. So you have user application, you have job submitter, job tracker, name node back and forth, Hadoop task tracker back and forth, holding tasks, and then it starts, a task that's super GM, and back to the HDFS node, all this stuff. With in-memory accelerator, this is the blue line. This is the only connectivity that you have. Because what we allow you to do, allow you to be embedded processing. So essentially, you run your memory job in the process of your data. So that there's absolutely no challenge about getting the data to the memory stuff itself. And I'll have a little bit more about it. This is very interesting. It's a very high-level overview, but the picture on the right is probably the best depiction of what we can do. And all of this overhead and all the complexity of Hadoop deployment goes away. Think about this, you don't need anymore the naming node. How cool is that? Because naming node is the most powerful part of complex deployment. You have to basically, have redundancy on the benefits of deploying this. Today, with GridGain-In, no naming node at all. You don't need to do a much better system. You share the entire metadata across all the nodes. You're naturally backed up in this data. Before I jump into details, just a quick picture about where the in-memory accelerator fits in the whole picture. So as I mentioned, the GridGain develops what we call an end-to-end memory computing platform. So the memory accelerator is just one product. We have quite a few others, C database, stream. The reason I want to show this slide is because the memory accelerator we had to really we didn't just develop for maybe 1 year in processes, huge amount of code. But we used a lot of technologies throughout the whole process in our ecosystem. Clustering, all the MPE processing, all the memory database, and data storage. Just to give you the size and perspective, we have about 5 times bigger than the entire Hadoop system because of the code base. So it's a fairly big project, and it's not a simple one. So with the details, I'm going to step on this slide for quite a while because I don't want to jump to the slide. I just want to give you this little look at the overview of what's happening underneath the hood. So on the right side is a diagram of very typical canonical diagram of the kind of stack layer. On the top side we have business apps, on the bottom we have system and GDM, and in the middle we have video. So one of the coolest features of what we do, and probably differentiates us quite a lot, is that we allow you to complete line of play integration. one thing we definitely want to avoid is to ask you, customers, to give your place. A lot of customers here to us, we have a headache. We actually don't want to replace it anything. Can you actually make it faster with whatever technology you have? And that's what allows us to do. We absolutely integrate with Hadoop. We install the same model. We don't have to provide anything new. It works right there. We support any Hadoop distribution, not limited to any Hadoop distribution. Whether you like Hortonworks, Cloudera, Netbar, Evago, Spotify, anything you like. We support both version 1, version 2 branches. So practically any Hadoop distribution you have in the world. In-memory file system is probably the biggest feature we have. As I mentioned to you, is 100% compatible with GFS. It can be used as replacement, can be used as an intelligent cache layer. We usually call it a secondary file system coupled with primary GFS. It can work in dual mode. We support probably very uniquely asynchronous and synchronous read through and write through. Very cool feature that essentially allows you to have no UTL in this file system. You do not have to copy data to GridGain-In storage user. You can install and complete the data empty, and it will automatically read through and write through HDFS in the frequency session mode. And essentially you're going to have all your hot data in memory, your memory used to work on. Another interesting feature that we have a block level cache. Like most of the products, we actually have a file-based cache. We have a block level cache. It's very interesting and important feature because there's a lot of localities in how files get accessed. Obviously, it's counting files at a time. Localities, pretty much the same across the file. But if it's service, if you have other processing of the file, there's usually locality. And in the block level cache, is a lot more efficient. There are a lot of prefetching file systems. Actually, if you're scanning files with a prefetching, the master data will be about the scan. There's no establishment. Very much the same feature in GFS. The coolest thing about it, one of the coolest things we have is this background fragment master. Think about this. It really allows you to have extremely fast writes in our file system. What we discovered is that essentially what allows you to do frankly, is every write to the file system is local. It's very fast. Then in the background, we defragmentize it to make sure that the proper partition goes to the cluster of nodes. And that allows you to have extremely fast runs without losing any consistency. We added that in Java framework, we have both on heap and off heap storage, so you're not even just Java heaps. If you have late or 120 gigabytes, gigabyte of RAM, we're going to use it all. So we allocate it. It needs to RAM heap and the rest of the off heap and then the entire file. Memory data use. One of the biggest things about memory use is duplication in the same process. It's one of the biggest we that you can get performance wise. To allocate your processing and your data in the same process. So there's no inter-process communication out there, there's nothing else. It's literally in a pointer-oriented way for accessing the data. And that's what allows you to do. Instead of like Hadoop does, essentially spawns up, a process where it can be, everyone has very awkward, configuration property. We, by default, allow you to run multiple memories to adopt the same GDM process. Properly versioning, properly gospel, and all this adapting mechanics properly by us. It's the biggest we. It's basically where you win most of the time. The biggest percentage. So we eliminate unnecessary IT communication with the same load. We eliminate multi-task startup times. And the interesting thing, if you guys are familiar with how the average works, is an mandatory step of sorting or shuffling or reduction step in the different averages. I would say 90% of jobs and tasks will need this. But it's pretty awkward to disable. You have to literally plug in your own operating sorter. We don't have that. Our average is record based. So unfortunately, we may have a key value processing, which most of the time we'll need. So we eliminate that as well. It's by default working faster because of it. This is a good detail overview. Other than we should have time to dive into much details, but this is a good overview of this. Projects like that do not exist without good DevOps, without good management of mind work. So we spent a tremendous amount of time building what already advisors, which is a unified management of mind work for all our projects. Just a few kind of screenshots, we have a pretty support for any man illustrator can do. So we have a full-blown file manager. It's very important because with us, you tend to work on the file system, because you're fast, local file system. So we give you a very nice file manager, immediately after functionality, you can view files, start with everything you do, and you know the file manager. The coolest thing probably is that you get profile. Because we're dealing with a dynamic file system, we're going to give you as much information about how the files are accessed, what's the speed, what's the, how the blocks within the file are being accessed, which blocks are being accessed, how the speed and all this performance increase, not very visible, but on this slide. Very useful too. They try to analyze which files, which folders you want to put in memory. Because actually memory is less capacity than our user space. So it's typically going to put all data in memory. So we give you full flexibility. Not only select which files are going to go in memory, we give you all information here, statistical information, and micro information about making it properly. Which files access how different, which speed access, all this different information. Pretty cool stuff. I don't know any other project, a little bit CDM from out there, they have a little bit more functionality because we're managing the entire ecosystem and we still going with that. But we're complementary to them in this sense. And this is pretty much real-time information. It's not a web-based, that's the app that gives you second-by-second updates from cluster of 100,000 nodes. Pretty cool stuff, I wish you could have that. Some of the benchmarks. This is a straight benchmark of the file system. We're running on small blocks of templates. Very much commoditized. Those days can be bought to grand on eBay. Very simple, nothing special. It's an 8 ports to use, including Java 7, typical network. Look at the numbers. File scan, almost 2,500% faster than the typical file scan. Creation, about 10x faster. Random access 700%. Deletion is what? About 750. And basically, how many other benchmarks? That's what you get when you remove the disk variable and you just keep that in memory. You get fairly sizable boost just on the file system operations. And it doesn't account for memory use. I would say the majority of the boost over the entire memory is just getting from the memory use location, not from the EHFS. EHFS probably is about 15-20% of the overall savings you get. So even that's pretty impressive. Well, we get this question asked almost every time. So Spark is somewhat similar to what we're doing. It's a great project. I highly recommend you look at it. There's an approach a little bit differently. I think the biggest difference for us is that Spark requires you to ETL data into Spark. And that's the architectural decision they made. So if you have an idea, you can install Spark on the left side, and have detected that and remove the Spark, then you can cross the Spark. We specifically try to avoid this without being in the file system, because really that's pretty opposite, because the Spark cannot process like it. You constantly have to ETL back and forth. Moreover, changes that you make in Hadoop, HDFS, no effect Spark. Changes you make in Spark, no get transferred to the Hadoop automatically. With us, there's no ETL. It's the same data. It's specifically designed a system so the builder has to move the data. Whenever you have data in Hadoop, keep the data. We're going to do the rest of the work and we use tools to process very quickly. We have a third block caching. Spark has file caching. And actually, this is very important. Think about this. We have thousands of 20 gigabyte files. Sometimes it's a very crude way of caching, just caching each 20 gigabyte file. It's a lot more convenient to be able to cache block by block. Because again, most of the time, you have some locality within the file how frequently it's accessed. That's just constantly scanning all the files, which almost never happens. You always have locality, and therefore, if you cache the entire file, you cache them out of the list. When you do the block, pro block caching, you utilize your memory, which is very successful, which is very much more effective. Now, the interesting story is that I was in the house 20 minutes ago, it shows you struggling out. Nonetheless, you should probably, I think we're kind of moving in the same direction. Let me finish this, I'm going to be very quick. So I'll give you an example. We're working with a customer right now. We're trying to get the name. It's a power company, we all know, in the big data space. So they have a very simple task. think about this. I think we all can relate. It's very like about speaking because it's simple. Everybody can relate to it. They're trying to use certain law files from averages to that's canonically use cases together. Data size for small is about 5 terabytes. I'm not talking about terabytes in Yahoo scale. It's predominantly write-head system, so things get read this the HTTPS constantly. And what they want to do, they want to have perceptual real time, essentially, at the bottom 2 seconds to everything else. So they come back with growing gross distribution, and it doesn't matter how they do it, but that's the case. And it basically saying a big challenge that overall job for this particular piece in this environment is about 40 nodes, 40 servers. So very simple. It's about meaning. The average order itself is about half of it, about 30 seconds. Data scanning, the level of scanning is not being improved because basically keeping the limit of the I/O. No matter what they do, they keep the limit of I/O, and the whole scanning is pretty slow because it's a constant I/O in this thing. So basically, we work with this client and we introduce in memory Hadoop acceleration and some of these things we've done. So remember this picture again. This is not the picture report for that. So we remove the name node. We install GridGain on exactly the same nodes. You don't have to buy anything. You don't have to report anything. We don't know what they have to have. Just install GridGain on the same node. And start doing data node on every server they have. They were able to, using our HTTPS profile, really look at the files that they needed to. And for this particular file, we just picked out this specific folder. It said every file in this specific folder needs to be in memory, so they can take it pretty quickly. And we allow them to take which files go where. And now that they use our memory use for the files that they will store in the memory file system, to end result, from over a minute, we got about 3 seconds. Now think about it for a second. How do you make something that runs for 60 seconds to be free on the same hardware? It's not a simple thing. Same hardware, just a different type of software. Without moving data out of it. It's not a simple thing, and they're fairly amazed. But that's that's about GridGain, but more about the overall dynamic approach. That's how much processing capacity we actually have in our existing hardware. We just have proper software that can utilize it. Again, everything is same hardware, same result, just different software. And we went from mommy in 60 seconds to about 3 seconds. And that had a lot of change. It wasn't just fast, it really enabled them to have that business line product because before that it was very process. You press the button and it tells you to look at flying you, and it's great. Right now, press the button, you have results. It's just very different user experience, it's very different type of product. That's it for me. You can download this thing from our website. It's our website. You can download through registration. It's free download. You guys can try as much as you like. Give us feedback. We'll be here to get it. Thank you. Any questions?
Thank you. Interesting presentation. I didn't catch that part. How do you synchronize the memory data with one file or with the file system?
Yes, we have full modes, but two that are interesting. So we have a synchronous read-only writer, and we have asynchronous read-only writer. So if you want to have a completely synchronous synchronization between memory and fast, use synchronous read-only writer. It will stop performance naturally because it's synchronous. You have to wait. Most of the time, we find people don't really care if there's 3 seconds delay to manage to fast in memory. Because it's affected by self-reproduction. So most of our, better customers use in a sequence mode. And that basically gives you a window power of a few seconds where things in memory are not the same as minutes. If that's okay, you use that with maximum performance. If you need full synchronization, transaction synchronization, then you sequence and you will translate it across the HTTPS memory, but you get a stop performance. Any other questions?
I understand most of your examples about filling up memory. What about the cases where Hadoop is most the data stored for each base that has its own in-memory block cache?
Yeah, we thought about this, about a year ago, we started with the memory file system. We thought we're going to be able to optimize Hive and the image base. It turns out it's not. And if you look at how E models, if you look at how Studio works, you cannot, all of them basically ditch the macros and go directly to HDFS. So HDFS is fine, and we provide even faster HDFS, so it's good memory. But if you want to reuse the Hadoop scenario, reuse then it's so split. I don't want to be worried about it. It was never designed for it. Look at how it works. It's found the GDM. It pulls the jobs, the tasks instead of pulling. So there's so many architectural decisions that, if we start, taking memories apart, there's no point in maintaining, compatibility. So we don't deal with the, we can still run, Hive and deep in the memory file system. You're going to get roughly maybe 2x, 2.5 at the most. And typically that's not, and some customers will like it, some guys say, well, it's not enough. Because the mapper used to get about 10x automatically, and that's a very good story.
And so what is the size of the helium RAM recommended for better performance?
We don't really recommend it. It's whatever you have. Typically what we see people have between, I would say, 40 nanometer Hadoop. I would say 64 gigabyte probably will be the minimum point of RAM. We see Java runs with 20 gigabyte RAM. But then, to really have a sizable data set, you can stack up a lot of those plates. We internally, for example, inside GridGain testing, our plates have a 96 gigabyte RAM. Stack them out, stack them out, stack them out, and test it. That's a typical setup. So with 10 plates, you get about a terabyte RAM. So 10 plates, terabyte RAM. 20 plates, terabyte, and it goes.
You can increase the RAM.
Oh yeah, physically, yes.
It's going to be a lot of processes in the top.
Yeah, with 64 speeds CPUs, there's no limit to RAM. The question is what's the economic feasibility. So if you guys are familiar with the memory storage, memory channel storage, it's a pretty constant medium quantity flash to the D factor. So that's coming, but as of today, I think most effective is the blade with about half a terabyte RAM, close to about 15 grams per system. And when we did our calculation, that's probably the most effective, 5 to 10 terabyte RAM.
What security features do you offer identification for access?
Sorry, say again?
What security features do you offer identification and access?
Typically, first of all, we're offering encryption on the communication layer between the two, but we try to stay away from ACLs because usually we run within enterprises. So currently we're not offering ACLs to domestic clients. Say, look, what you have currently, we're not going to mess it. One is the application. We're going to do the last 3 or 4 years, and even right now, we guess pretty much not. So, literally, we go.
You think you could handle Knox and Aurelia?
Sorry, say that?
Are you could handle with Knox?
With NAS? Not in the line right now.
Okay, thanks.
Would you differentiate between HANA and your system? SAP HANA in-memory database?
Yeah, SAP HANA is a SQL-based memory column store. We have a competitor which is called the memory database. And I can spend probably several days to talk about that. And memory is not about that. That's the difference. Try to use HANA to accelerate value. What you can end up doing in the ETL, hopefully in HANA. That's about 5 hours. Then you can run SQL queries, which you can work fairly fast. But then you have to basically understand how you must play information fast storage to SQL schema. So that's a very different thing. And for that, we have many options. What we do, the key for us is to test not to use the customer and say, look, don't change it. You have to do not. What we do, we're going to plug in and make it faster. Don't ETL anything anywhere. Don't move anything because we're already tired of the hell of moving that in the world, right? We try to move away from ETL in Hadoop itself. Those different systems work with GFS directly. So we're not trying to ask you to do anything. You have how they're going to reproduce fast, keep on having it there. We're just going to plug and toggle and then catch what's needed if you're going to do this right and run very fast connectors on that way. And most importantly, we don't ask you to do everything. Move only the files that you care about. Move only the payloads that you really want to be fast. Not every payload is a real time to do. Again, it's changing animation. You know, in our estimation, maybe only about 15 to 20% of payloads really need to be fast. Because it is, it's a dead warehouse. Nobody's going to want everything fast. But those 15 to 20% of payloads you want to run